Let us study about vibrations of air columns and organ pipes. Organ pipes basically hollow pipes which could be open at one end, or these pipes can be open at both the ends. If a pipe is open at one end, called as a closed organ pipe because it is closed at one end. If both ends are open, it's called as open organ pipe. This pipe would contain air particles in it, and then these air particles can be set into vibrations based on an external frequency. In this case, we get different kinds of. Let us look at it one by one. First, let's look at closed organ pipe as seen here. There are many examples of closed organ pipes. An example could be like whistle, where one end is closed, other end is free. If air is blown over the whistle, sounds are produced, and we can get different frequencies in the case of closed organ pipe. So first consider that there is an organ pipe of length L. Since one end is closed and other is open, here we get stationary waves. This is because there will be one wave which travel in direction, other wave would reflect through the closed end and travel backwards. So two waves traveling in opposite direction would superimpose, giving us standing waves. The simplest possible would be case where there is only a part of the loop. Now in this case of a closed pipe, the closed end would be a node. The open end cannot be a node, it will be an anti-node. So we know that the distance between two nodes will be lambda by 2. Distance between a node and an anti-node would be lambda by 4. So the distance between two nodes is here. We'll take a simplest case where there is node at one end and other end is open. So what we get here is we get 1/4 of a wave. Means the length here contains 1/4 of its wavelength because in earlier the distance between a node and antinode is lambda by 4, and velocity is equal to f into lambda, means frequency is equal to v by lambda. So here fundamental frequency, which we call as f1 is equal to v by lambda, where v here is speed of sound in this medium, which is air in this case. So f1 is equal to v by lambda 1 is equal to v as it is. Lambda 1 from here would be 4 times this f1, which is equal to 4 v by 4l, called as fundamental frequency. Fundamental frequency. To find next frequency, we can take a case where we have a half loop, because we have one loop here, a half loop here. That is, one point is node, this would be an anti-node, then a node, and then an anti. Distance between this and this is lambda by 2, lambda by 4. So the distance between this node and this antinode would be 3 lambda by 4. The wavelength will be different in this case compared to the previous case. So it's again wavelength is the length L. That length L here is length of the tube. That length contains 3/4 of different wavelength. This implies lambda by 2 would be 4L by 3. Therefore, fundamental frequency Therefore, the frequency in this case is f2, that is v by lambda 2 is equal to v as it is, lambda would be 4 L, 3 goes on top, 3 times v by 4L, but v by 4L is called as the fundamental frequency. Therefore, f2 or we call as f3 just to keep first consistent, or as f3 here, no difference writing the notations here, but just to keep it consistent, write f3 here. We'll consider lambda 3 here, f3 is equal to 3 times. Similarly, if we look at the next case, then the points would be like, we'll have complete wave plus quarter of a wave, because the open end is always antinode. So just recap it. The first case is a node, then anti-node. Next case would be, this is a frequency got f1. Case is a node, anti-node, a node. Here the distance between these two was lambda, it will be 3/4 of this wavelength. So if you call it as lambda 3, it will be 3 lambda 3 by 4. Next case would be a node, anti-node, node, anti-node, node, and then anti-node. So distance between this and this would be lambda. This would be lambda by 4. Since it is different wavelength here, we will call this as lambda 5. This notation. So here, if we extend the same argument here also, then the next frequency what we would get would be f5 will be 5 times f1. So what is seen here is, what we get is, we get f1, then we get it as 3f1, 5f, so on. This is called as this third harmonic or first overtone. This is called as fifth harmonic or second overtone. So what we find in this case is, we find in this case the ratio of frequencies is 1:3:5. Goes like this. In case of a closed pipe, what we get is only odd harmonics.